Hi guys, Zeno here. Shout out to all you physics fans out there, because today we're going to do a physics video. And the problems is as follows. So suppose we have a disk that's rolling down an inclined plane as shown, and the disk has radius r. So there are two questions here. The first question is, at any instance in time, does there exist a point on the disk that has instantaneous velocity equal to 0? So does there exist a point with velocity equals 0? And the second question is, at any instantaneous point in time, does there exist a point on the disk with instantaneous acceleration equal to 0? So problem 1 is velocity equals 0, problem 2 is acceleration equals 0. So take a moment to think about it, and let's get started. So problem number 1 is quite a classical problem in physics. If you've ever taken a physics a course before, you've probably met this before. So the main idea here is that the tangency point right here always has instantaneous velocity equals 0. There's two ways to really think about this. The first way is to try to describe what exactly is the disk doing when it's rolling at an instantaneous point in time. So we sort of think of rolling as rotating about the center of the disk, but in fact when it's rolling down a plane with no slipping, I forgot to mention that, there's no slipping for the disk. If it's not slipping, then that means the contact point is going to be touching the inclined plane, and the disk is going to be rotating about this tangency point. So if you sort of imagine the rolling motion of a disk, you can kind of see it as rotating about this tangency point this way as an instantaneous move of the disk. And then the next moment, it'll have a different tangency point, say here, and then it'll have a rotation around this pivot point, and then so on and so forth. It rotates about each of the new pivot points that are formed when they become the tangency points. So if you view rolling like this, it's clear that this point right here, it has instantaneous velocity equals 0. An alternate way you can think about this is by thinking about the net velocity. So let's say that the velocity of the disk at a certain moment is v, going down. Now the question is, what is the velocity of the edge of the disk right here on the bottom? Well, since the disk is rolling without slipping, if we look at the rotation from the perspective of the disk center itself, it looks kind of like the ground is moving backwards at a velocity of v, so that it's rolling the disk with this fixed center. So in fact, the disk itself is moving forward with a velocity of v. The ground is rolling this bottom point backward with a velocity of v, so therefore the net velocity is going to be 0 on this point. Now here comes the more interesting part. Does there exist a point on the disk with net acceleration equal to 0 at any instantaneous point in time? So do you have any guesses on where this point possibly could be? Well, unlike the velocity where the point is a very well-defined place, it doesn't really seem like there's any easy way to visualize where this point can possibly be, if there even exists a point. So instead of trying to figure it out intuitively, let's try to look at the different accelerations that occur on each point and try to see if we can somehow find a point such that all these different accelerations all happen to cancel each other out. So let's take a look at a random point. And let's say that, let's call this actually big R, because I will call this length small r. Alright, so what accelerations are happening on this point at an instantaneous point in time? Well, first there's, of course, since the disk is rolling down the ramp, there will be an acceleration going down the ramp. So this is the linear acceleration going down in the direction of the ramp. So, of course, that's not all the acceleration that there exists on the disk. There's also centripetal acceleration. So centripetal acceleration will be pointing in the direction, in the opposite direction, well, in this direction here, right here. So this is the direction that centripetal acceleration will point. So is this all? Well, there's actually one more acceleration that we haven't taken into account for, and this is because since the disk is accelerating down the ramp, its rotation itself is also accelerating. So we also have this third acceleration vector right here, which is the acceleration of the actual rotation. So we have 3 different accelerations here, and we want them to all add up to 0. But these seem pretty hard. I don't really want to calculate this by brute force because I'm lazy and it doesn't seem very easy to do. So I need to somehow come up with some sort of easier way to visualize this so that I can actually find such a point, if it exists, as easy as possible. So let's start out by recalling the formulas for each of these accelerations. So first off, let's consider the linear acceleration. Well, let's just let that be A because we don't really know much about it. Just since it's at any point in time, just call it A. Next, we have centripetal acceleration. So remember that centripetal acceleration is given by the formula v squared over r. Now v squared over r is equal to omega times r. So that means when we square it and divide by r, we get the other formula, which is omega squared times r. So this is the centripetal acceleration. Finally, we have the tangential acceleration. And what might this be? Well, the tangential acceleration is equal to alpha times r. And alpha times r, well, alpha is just equal to the linear acceleration, which is also the acceleration right here by the same reasoning as the velocity part of the problem. The linear acceleration divided by big R, the radius of the entire disk. So that means this thing is equal to A over R, big R times small r. Alright, so we have these 3 formulas for the magnitudes of the accelerations, and somehow we need to add them up to be equal to 0. Except for there's one small problem here. First, we seem to have a heck of a lot of variables, and second of all, these acceleration vectors are not all pointing in opposite directions. Adding them up is not going to be a straightforward task. So how might we try to make this a little simpler? Well, let's first try to add them up, just geometrically, not actually algebraically. So first off, we know that there's a right angle here, since centripetal acceleration and tangential acceleration are always right angles. So what else do we know here? Let's say this is omega squared r, this is A over r times r, and this is just A. So something we notice here is that both the centripetal acceleration and the tangential acceleration both are linear with respect to r. So that means that if we take r to be 0, they're going to both be 0, and if we take r to be big R, then we're both big R. And if we pick anything in between, then they're just going to be whatever their sum of their vectors is times some sort of constant that's between 0 and 1. So this gives us the idea that we should probably combine these two first before combining with this random A right here. So if we combine these, then we get whatever vector this is, but the important part is that it's linear in R. So if we take it at 0, it's going to be 0. If we take it at big R, then it's going to be some other value. So how does this help us? Well, instead of 3 vectors, we now have 2 vectors. And in order for 2 vectors to add up, well, that's easy. We just need this vector right here to be the negative of A. So how do we do that? Can we even guarantee that ever happens? Well, for them to first add up to equal 0, we need to first match up their magnitudes. I don't really want to calculate explicitly the magnitudes here, so Instead, I will use a continuity argument. So if r equals 0, if small r equals 0, then that means, let's let this be a prime. Then that means the magnitude of a prime, that's magnitude of a prime is also equal to 0, because plug in r equals 0, both of these vectors, centripetal and tangential acceleration, are both equal to 0. Well, what about on the other end of the spectrum? If r equals big R, then that means the size of a prime, well, I'm not quite sure what the size of a prime is. I don't really know if I want to know this, but the good part is that since the size of a prime is greater than or equal to the size of the tangential acceleration, and this is equal to, when we plug in r equals big R, a itself, then we know that the magnitude of a prime when r equals big R is going to be greater than or equal to the magnitude of our a right here. So that means that since if we go from r equals 0 to r equals big R, the magnitude of a prime changes linearly from 0 to something bigger than the magnitude of a, then that means somewhere in between we can find an r equals to some r0. I don't really care, such that the magnitude of a prime is equal to the magnitude of a. So we're halfway done here, and all we need to do now is to match up this angle so that it's 180 degrees. And how do we do that? Well, that's actually a lot simpler than you might think, because remember, this point, all the calculations I've done so far only depends on the distance of this point from the center. It does not depend on this, where the point is on this circle with radius r. So that means that if these two vectors don't match up, we can just rotate this point to, say, another point here so that they do match up. Their magnitudes we've already guaranteed are the same, so, and since this rotates an entire 360 degrees, there must exist a point on this circle such that not only do the magnitudes match up, but the angles, the angle between them is 180 degrees. So at this precise point, the net acceleration of that point at that instantaneous point in time is going to be 0, as we desired. And note that this not only shows that there always exists a point on the disk at any point in time with instantaneous acceleration 0, it also shows us that this point is actually unique, because this r equals r0 is going to be unique because of continuity, and this thing grows linearly, so it's going to be bijective. So there's going to be only one r0 such that this works. Furthermore, there's only exactly one point on the circle with radius small r such that a prime and a are going to be completely different directions. So there's actually exactly one point such that the instantaneous acceleration is 0. Today we're going to talk about Hall's marriage theorem, and it goes something like this. Suppose we have some number of boys. So I don't know how to draw people. That's good enough.